People also wants to know about ASICs, how ASICs is different than FPGA. So we'll touch on that aspect also. So the agenda will be the FPGA introduction. I know if you go and find the FPGA definitions or want to understand what FPGA is, I think all the Googles or all the links, it will not, it will make you confused. But doing some study and doing some research and my personal experience, I have made it a very simple and a very easy explanations to understand the FPGA. We will understand what FPGA is. Then what is the design flow when we talk about FPGA? So it is not as simple as MCU. There are different design steps that needs to be taken care for the successful FPGA design project. We'll walk through the design flow, and then as I said, yeah, we'll understand in what aspects MCU is better than FPGA, for which application we can use FGA, and then for which application MCU is better, we will understand. And yeah, of course, I think example is the best way to learn anything, because that gives you kind of sense and kind of a vision how we can use those devices in the particular applications. Now coming to FPGA, right? If you see the today whatever the device is, right? We want every device to execute the instructions or executes the lines of code or the or process any a kind of task very fast. We want every device to be fast. We want it should have a lower latency in terms of delays. It should not, like if we are using any if you are developing any time critical, right? Time critical, let's suppose some edge device, you want to process data and then immediately transfer to other, so you don't want any delay there, right? Some mission critical application where you want a fail safe kind of hardware, you don't want your hardware to malfunctions, or kind of you want a higher compute performance, you want a lower power. I think in everywhere, whether it is a ADAS in automotive ADAS or in medical applications, you are processing images, right? You want a better clarity, better resolutions. You can you want a diagnosis on that image, or even the cloud applications, or even the kind of now computer vision application, right? Everywhere you want a more compute power, lower power consumption, better performance. In that aspects, yes, there are different architecture that is there available. We use a pipeline architecture, we use a superscalar architecture to achieve those speeds, those lower latency, and so in that aspects, FPGA also comes in those band those spectrum. So FPGA can be used for those applications where that is a time critical, you want a lower latency, you want a reconfigurable hardware, so you can configure the hardware at any place for any application for any functionality, and yeah, of course, a better performance. So you can see like how FPGA is really impacting all the industry. For examples I have mentioned, you can see like the AWS, which is a cloud, they are using FPGA for their computing service. Even Microsoft Brainwave, they are using FPGA for deep learning. So you see in what kind of applications the FPGA are getting used. The high speed video processings, the accelerator, whatever the accelerators are there, like you take a videos or image, you do some kind of inference means kind of a decision making. So for the hardware accelerator you are using FPGA. You see Microsoft Bing, those search engine, they are using FPGA, the Alibaba Cloud. So you see in what are the industries and the very complex applications, how they are using FPGA in their design. Of course, they are using because it has pros, it has a benefits, and we will try to understand the benefits in upcoming slides. Uh, Coming to the market size, if I want to talk about market size, you can see like how year on year growth it is happening. You can see 2022 the market size was about almost 7 billion, and the expected for 2029 is about almost $13 billion, which is CAGR is 8.6. So year on year growth is 8.6. And industry wise or application wise, you can see, right? The consumer electronics we are using much, even the industrial, automotive, military and aerospace we are using FPGA. Data processing, telecom, we are using FPGA. Some of the projects where FPGA are used, some renowned project like LEGO, which is nothing but a kind of a wave detection. You can search more about this. Uh, they basically detect the gravitational wave, and they are using FPGA in their projects. Satellite applications, they are using FPGA, which was a SpaceX Falcon 9 rocket. They use FPGA for defense electronics telecoms product. We have been FPGA. So this gives kind of a motivations, like what the wide spectrum uses of FPGA in the industry. And let's go with that. We'll understand the FPGA introductions. So these slides mainly talk about the unprogram and program logic device, because before going to FPGA, I would little bit give a brief explanation of what do you mean by hardware programmable, and what do you mean by hardware unprogrammable. So if you see this, the left logic circuits, right? So here you can see this is a AND gate, and this is a OR gate. Basically we call it, this is nothing but a kind of a PAL, programmable array logic. And the programmable array logic, basically we have a C, we call it is a C or array of AND gate or OR gate. So what you see here, there is a buffer, right? You have an input ABC, right? And you also get the inverted output out of this buffer. So one is A, you also get inverted. But what you see, right? This AND gate, right? This input coming to AND gate, and from the buffer, right? They are not connected. It means this hardware is not giving any output. If it is not giving any output, right, of course this OR gate will not have WXYZ. These are the output of OR gate. They will not have any output. It means we call it as a on program hardware. I am not saying on program software. So let's not talk about software. That is where many people get confused. Let's talk about hardware only. Because these are logic device, these are nothing but the transistor. So it is a on program. Now what is program then? So if I connect these lines to these lines, right? If I see this first, so this A, B, and C. So this AND gate is doing nothing but they are taking this input from buffer A, B, C and giving the output A cross B cross C, and same way this AND gate, A and C, B and C, and again here we are connecting the lines, and then we are getting the output. It means this hardware is programmed now, okay? And the same concept we are going to use for FPGA to understand the FPGA. So that is why I thought before going there, I would like to give a brief kind of explanation what is program hardware and unprogram. With this, if we want to understand the FPGA, right? So FPGA stands for Field Programmable Gate Array. When I say field programmable, it means after the chip is manufactured and by the vendor, you can program it or you can reconfigure this FPGA device anywhere. Where you are working in the lab, you are at the customer site, you are at like any place, you can reconfigure it. That is why we are calling it as a programmable. with these words, I am little bit not like convinced field programmable, but reconfigurable, because you I will tell you how what reconfigurable means you can reconfigure the hardware. And the gate array, because there are the array of a sequence of gates, logic gates. That is why you are calling it as a gate array. Now with that, before understanding more, let's understand the traditional logic device, how it used to be. So maybe in your college days, or in your practical digital electronics practical session, you must have used this breadboard. And you can see this is a breadboard, and these are some logic gates like AND gates. These are some OR gates, or some combinational logic device. And you see these wires, right? So kind of this was a traditional or logic device. Now how it is, this we used to be the logic device, which used to perform the logic operation like AND or NAND, right, NOR. And then these wires, right, connecting from one logic device to another, these are nothing but, you call it as a programmable switch matrix. Okay. And here, right here, you can see here we used to connect some peripheral like LEDs or switches. These are nothing but a IO block, right? And whatever this breadboard we see, right, they are internally connected, right? We call it as a kind of a connection line, which is like a single, double, or direct line. And understanding these, we'll try to understand the modern FPGA device with all these, right? You have a logic device, and then you have these wires connecting from one logic device to another. Then you have these IOBs, input output block, where you connect your LEDs or any peripherals. And then these lines, connection line. Okay. With this, what I can say that the FPGA device, right, it contains all these elements what we discussed now. They contains the configurable logic block. Okay, we'll try to know what is this configurable logic block. And then it has a IOB, input output block, where I told that you connect your outside world, like you have your motors, you have sensors, you have LEDs anywhere. Now this CLBs is getting connected to IOBs with this interconnects line, like, right, interconnects lines, what you call this connection line. And then how this CLB is connecting to this CLB using this switch matrix, right? This is my switch matrix. Okay, these lines wire I told you, right? So a normal FPGA device has these elements: logic block, switch matrix, input output blocks, and the connection line. Okay, so you can see FPGA is made of configurable logic. We also call it as a adaptive logic model. Some DSP blocks are there, some RAM blocks are there. We'll try to understand what those are. Another aspect of this field programmable is that you can change the functionality of the device. As I said, it is a field programmable. You can configure or program this FPGA for any functionality you want. Okay, you might be thinking, oh, you can do for MCU also, but we will try to understand how it is different. So for now, let's focus on this. So functionality inside the device, right? It can be changed. How it is getting changed, right? Let's try to understand. So you can change the functionality inside the device by configuring the hardware. So you are not changing the software, but basically what you are doing, right, you are configuring the hardware. You are changing what blocks to use, right? We'll see in detail what blocks to use, right? Which switch matrix to use, what input output blocks to use. So basically these are nothing but these are having some transistor. I will in next slide I will talk about. So basically you are changing the functionality by changing the hardware. Okay, And what is that hardware? By changing the what flip flops you are using, what logic gates you are using, and how these gates are being connected. Okay, using this switch matrix, you are changing the functionality. And other yeah uh, with that, let's understand each of these blocks. CLB is switch matrix, input output, and then connection line. So if I have to talk about this configurable logic block, so what you see here, this is a simplified logic cell simplified, where you can see there are two slices and they are connected to the switch matrix. I told you right here, the CLBs, each CLBs are connected to switch matrix through switch matrix. Okay, so CLB is nothing but it has two slices. I will talk about what slice means. Okay, so it contains two slices and they are connected to the switch matrix. And now what is slice? A slice is nothing but it contains your lookup table. Now you might be worried what is lookup table. I will tell you about that. So it contains a lookup table, it has a flip flop, it has a multiplexer, it has some arithmetic logic units. Now let's understand what slice is. So if I want to describe the slice, it looks something like this, where you can see the function generator. Now you must be telling what is function generator. I will talk about. So it is, this function generator is nothing but, people call it a function generator. They also call it as a lookup table. Lookup table. So they are used interchangeably. So you can call it as a function generator or lookup table. It is same. So you see this slice is containing the lookup table. There is some mux. You can also see this, there is a D flip-flop basically for a delay, to create a delay, and there is some kind of control circuits you can see, right? So this slice is nothing but this contains these elements. Now what is this lookup table? So lookup table is nothing but it looks something like this. Okay, it is something like this. I'm just trying to explain in a better way. If you have done a digital circuit, and if you know something about when you do the sum of product or product of sum using k map. Okay, so you do right, like these are the inputs a b c d, and then you simplified it, right? So function generator is nothing but these box are there. These box are is the lookup table. So whatever the box contain the value, it is stored in this function generator. Okay, now what is this box? What is this box? This box is nothing but SRAM cells. Okay, so the lookup table is nothing but kind of a SRAM. Okay, where these whatever the values are there inside this box, these are stored in this SRAM. Okay, this SRAM. So lookup table is essentially a RAM. Okay, usually you can see a 4 input LUT or 6 input lookup table. Okay, and as I said, lookup table is nothing but essentially a SRAM. So based on the input, they have those address line, whether it is a 4 input or 6 input. It has for a now you consider it as a 4 input LUT, where there is a 4-bit address line. Okay, and once a user, right, describe a logic circuit either through hardware description language or through schematic diagram. Now what happen when you describe the logic, right, whatever the logic, so the FPGA software, right, they will automatically calculate all possible results, these results. Okay, and then it will write those two table into this RAM. Okay, so this is nothing but this function generator. Okay, it means, let's suppose you have to implement this. This is the Boolean equations. This P is a function which is the function of A, B, C, D, right? You can see. Now I have to implement this using this configuration logic block. So how you can implement? You see how it is implemented, right? This is A, P, this is a function, and plus A dash P, this is a function. We can write this as a Q, right? BCD plus A dash R BCD. Okay, so how it is happening? So here this equation, right? Here this q bcd, four input, right? These are four input, these are four input lut. So this q function, it can be implemented using this lookup table, okay? Lookup table g, okay? Now this r, right? This r bcde, it can be implemented using f. Oh, someone join. Hello. Yes. So okay, so I was okay, so you can implement this function BCD using this lookup table, and you can implement this R using this lookup table, and the other, right? A now it becomes AG plus, right? This P is equal to AG plus A dash H, right? This AG. So this you can implement using lookup table H, this function, okay? Because this is nothing but this, right? This is, you consider this as one as a block and this as a one. So you implement this in this using G, and you implement this R using F, and then you implement this together using LUTH. It it means you can implement any function, any Boolean equation using this logic block. This is how it is designed, right? You have a lookup table, you have a flip flop, you have a multiplexers, so you can output the directly output from LUT, or you can output through delay if you want a delay, or you can select any of these using this multiplexing, okay? And this lookup table is nothing but a kind of a SRAM cells. So whenever you describe the circuits or logic, so your FPGA tools does nothing but it writes whatever the output are there, right? They write into the SRAM cell, okay? So this is what we are calling as a configurable logic block, or you can say as a configurable hardware. Basically you are changing the functionality, okay? You are changing the functionality by selecting what gates you are using, by selecting what flip flop you are using, by selecting what mux you are using, and by selecting the interconnects, which flip flop is connected to which gates, okay? So by basically changing the hardware, you are changing the functionality, okay? I don't want to bring software because that will confuse you, okay? So basically you are configuring the hardware. So this is CLBs. Now the programmable switch matrix, okay? So if you see these CLBs, right? This CLB we already spoke about. Now this, if I am writing any logic, right, where this I am supposed to use this logic and this logic, right? So how this logic will be get connected using this programmable switch matrix, okay? That, because you just understand why you are talking. This is a programmable, I am saying it is a programmable. It means it can be reconfigured. You can reconfigure this switch matrix, okay? You can connect this CLB to this CLB to this using this switch matrix. Basically you are programming this switch matrix, and how you are doing it, we'll try to understand. So if I try to give some more detailed view of this PSM, it is nothing but it looks something like this, okay? You can see these are the single lines, okay? And these are the double line. Double is nothing but the differential line. You see here differential line, and these are the single line. So there is a row and these are the column, right? And you see this dot, each lines row and column are connected through this dot. These are nothing but we call it as a diamond switch, okay? And what is the diamond switch? You see diamond switch is nothing but it looks something like this, okay? Now let's understand a more in detail way, right? What is this PSM? So if I want to give you the some inside logic inside this PSM, it looks something like this. You have a SRAM, right? SRAM cells, okay? And then those SRAM cell is enabling the pass transistor. If you know the pass transistor, right? So it is nothing but whatever the inputs are available, if the gates are on, whatever the inputs are available, it will pass to the output, okay? And how you are enabling it? With the SRAM, okay? And as I tell, right, whenever you write the logic, right, the tool write the truth table back into the SRAM. It means once you describe what CLBs are connected to this, you are doing nothing but what you are trying to do. Oh, this SRAM you want to make it on. So basically, the tool will write one over here. Okay, if this is a NMOS transistor, if you provide a one, this will act as a this will be on. Okay, so whatever input will be available, it will be available at the output. So this is how it is connected. Okay, this is the logic cell, right? And these are the pass transistor. Okay, switch matrix is nothing but a kind of a pass transistor. So you can see that this is a pass transistor, here is a pass transistor. So this diamond switch is nothing but it has a 6 pass transistor. Okay, over here, over here, over here, over here, and then one over here and one over here. Okay, 6 pass transistor. And that is how we are programming. So this we call it as a programmable switch matrix. Now other is a configurable IO block. Okay, so as I said, now whenever you are you have a FPGA, right, you want to connect these different peripheral to these FPGA input output pins, right? It can be your LEDs, it can be your motor, it can be your sensors, or anything, right? You want to use for any applications. So what does it means? This is this is one FPGA chip, right? And these are the balls you can see, or I can tell you these are the pads. Okay, these are the pads, or these are the pins. And this pins is nothing but this is, right, these are the IO pins. And when I say configurable, right, it means you can configure it for different drive strength. I will talk about what is that drive strength. So input output pin, and it is something like this. Okay, it has something like this logic. Okay, you have some flip flop, some other driver circuits you have, right, amplifier, and some other driver circuits you have, right, to meet the demand of different IOs, right? Whatever the IOs standard are there, whether it is a CMOS or LVDS or TTL or ECL. So whatever the logic or whatever the device you want to connect, right, it should able to match those standards. So that you define over here. Okay, and it has those circuitries. Okay, so you can define as an input or output. Where you do that, I will talk about. So this is something like this. And you can see, right, these are the pins where I told about. These are the pins, and these are connected to these are the internal circuitry, pad with the gold wire. Okay, and then you have these buffers for inputs, and these are for outputs, right? So you can configure this iOS block to support various signal standards. Okay, as I said, LVDS or CMOS, or any LV CMOS or LV TTL. Okay, low voltage, and different protocols. Okay, enabling the FPGA to communicate with the wide range of peripheral. That is why we are configuring these IO blocks. Okay. So I think with this, as is in my application, I told we'll talk about CLBs, we'll talk about PSM, iOS block also, we already spoke. Now with this, let's understand what is behind FPGA. So if I really want to tell you what is behind FPGA, it is nothing but these are numbers only, bits, ones and zero. These are the bit stream, right? And as I said, right, these bit streams are being written in the SRAM cells, and then that SRAM cell is connected to the transistor. Like for PSM, I told about. For LU2 lookup table, I told you, right? Their lookup table is nothing but a SRAM. These are being written, right? And for IOSB also there are some similar kind of things. So it is nothing but kinds of bit streams. Those are configuring these all elements, and you are changing the functionality. Whatever you want, you can do with this. Okay, FPGA. That is why it is a very powerful. You see how it is, right? And how do you configure these FPGA? Using some flash memory, whatever the compatible flash memory are there, whether you are using a Xilinx, whether you are using a Altera, or whether you are using a Lattice. Okay, you can config I mean you can there are different flash memories, quad SPI, octal. You can choose based on the design guideline by the vendors. Okay, don't select anything like haphazardly. Okay, so with this, let's understand the FPGA design flow, right? Maybe it will be little bit of helpful for those. I think it will be helpful for hardware designer also who are designing any embedded applications using FPGA. It will be also helpful for someone who is writing the FPGA code or VSDL code, okay, or RTL code, okay. So let's understand. So you understood what FPGA is, what are the configurable logic block, what is the switch matrix, what is the IOB block. Okay, so you understood overall what FPGA is, why, how it works, right? How you configure FPGA for different functionality. With that, right? How how the flow design flow happens when you are doing any FPGA hardware, right? So you will have any requirement specification, right? Either from customers or either for any industry you are working, right? Whether it comes from your manager or anyway technical requirement. So you will have a technical requirement. Based on that technical requirement, you will create some kind of architecture. For examples, what here you can see, there is some external memory interface. Okay, it can be RAM or anything, and you want to read those or interact, basically interact or communicate with this memory using a FPGA device. Okay, so what do you do in FPGA? What you are doing? You are implementing all these logic block. You are implementing this FIFO. Okay, read, write, FIFO, and these are the commands. Okay, for reading and writing, and command for controlling. And how do you are using? You are using some XI interface. XI is nothing but kind of a chip to chip interface. Okay, and so you are using these all logic blocks inside your FPGA. Okay, so based on the requirements, you create architecture, kind of a block level diagram, how it, and then after discussing with all your stakeholder or architecture, the finalization of architecture, you go with the design entry, right? Then there are different ways for design entry. One is that you write a VSDL or Verilog code. It is nothing but a kind of a RTL code. Okay, basically, kind of you can use different tools. You can use a Quartus Prime, okay, basically from Intel, or you use a Vivado from Xilinx. There are other tool also for doing this VSDL Verilog. There is also another way, like you do the schematics. By that also you can do that. But for now, okay, let's understand that. Um, After your architecture is finalized, you can do the design using these methods. Writing a VSDL. VSDL is nothing but it looks something like this. Okay, you have a module where you define your all the inputs or the outputs, right? And then these are some signals, and then this is some logic function, and gate, or gate. This is very log. This is not VSDL. VSDL and very log syntax are a little bit different. Okay, so but people say that Verilog is a little bit easier because it looks something like C language. That is why it is easier. VSDL is little bit difficult. Okay, so you do the design entry using these. Okay, VSDL or Verilog. Once you do the design entry, right, whatever the code you have written, right, you do the behavior simulation. Behavior simulation is nothing but what you are trying to do, whatever the VSDL code you have written, and what was your requirement, right, or what was your design intention, right? So behavior simulation is nothing but you try to make sure that you want to simulate the behavior of this RTL or the VSDL, whether it is working as intended or not, whatever you have expected, right? If you are writing any full adder or half adder circuit, right? So when you do the simulation, you understand whether it is working as full adder or not. Okay, and for that you do the behavior simulation. So if it is working at if the working is okay, you move to next stage. Otherwise, you go and change the design. Whatever you have done, there must be something wrong. And you can, these are some simulations. You can see right here. You can see your input ABC, and these are nothing but kind of a value. You can see 0 1 2. Here you can see right here, like for A and B, the input is A 0 B 0, so you expect Z should be 0. So you can verify this using this behavior simulation. Once this is done, right, once this is done, you move to next step, that is synthesis. Synthesis is nothing but you understand it, whatever you have described this, right, using this boolean logic, right, you are translating those RTL code or VHDL code into the net list. Basically, the get level circuits. You see, whatever it was there, right? ABC, it is X. AC output was Y here. BC output was Z. It is here, and now you are using a OR. So it is nothing but this G4. So whatever you have written, synthesis is nothing but it's translate this logic into the get level netlist. Okay. Now, once this is done, once you have this netlist, right? Once you have the netlist, you do the functional simulations. Now you must be asking what is difference between these behavior simulations and functional simulation. Okay, let me tell you. This behavior simulation is nothing but what you are doing. You are just simulating the RTL code. Okay, so here what happened? The codes whatever you have written, it is not compiled. Okay, it is not fully compiled. You are just checking whatever the RTL code you have written, whether it is working as intended or whether it is working as expected or not. Okay, so here timing information, whatever the timing information is there, right, setup, hold time, slack, it is not considered during this behavior simulation. But whenever you do the synthesis, okay, you see synthesis, you are translating this RTL code into the net list, but you are also using some vendor library. Vendor library is nothing but kind of, there are some design constraint. So you provide some timing constraint, okay, to this synthesis step. So synthesis is nothing but it compile the full net, like it compile the full net list and also include the timing information. Because of that, we are doing the functional simulations. Okay, to check all the timing parameter also, as well as the functionality of the design. Okay, here in this system. Now if all that is okay, right, it is functioning okay, you have also looked some the timing aspects. If it is working as expected, now you move to the next step, which is a implementation. And implementation is nothing but it contains three steps. It has a translate, map, place and route. So each steps does a different function. So what translate does is it combines whatever the netlist was there. Okay, you generated the netlist, so it combines the netlist and the vendor library, whatever the libraries are there, like design constraint. Okay, you see here I have given one snippet. This is nothing but the design constraint or the pin assignment. Okay, you see here I have written like set property pin 33, you are connecting to C out. Okay, C out signal. Okay, set property pin H3, you are connecting to port S. Okay, so these design constraint you combine with the netlist, and this translate combine all these netlist and this design constraint, and then it creates a logic design. Okay, it creates a logic design. Now here basically you are basically here whatever steps you are doing for your target device. Okay, so you are doing for your target device. Now you have created a logic design. Okay, kind of you see like of this, you have created a logic device. Okay, now what happened, there is a map, place and out. Now map is nothing but, you see, now you want to use this logic blocks. Okay, this you decided that this means you are mapping now. Okay, you want to use this logic block, this there are different. Okay, but you can configure it what to use. Okay, based on whatever simulations you have done, timing whatever the delays considering all these blocks I am using. This is nothing but map. Now place and route. Okay, so uh, okay, sorry. So this is place and route. Okay, place and route is okay. Now let me talk about map. Okay, you have a logic design. Okay, now here let's suppose this was the function, right? X a dash b dash c d whatever it was there, right? So here, as I told about during configuration logic block, how you are going to translate this is called translate is nothing, map is nothing but we call it as a technology mapping. You are mapping the logic, right? So what lookup table you are going to implement this? So I here you see use lookup table f to implement x, use lookup table G to implement these all, right? So here you decide what lookup tables you are going to use, what function, what logic blocks you are going to use. Once you decide this is nothing but technology mapping. Now this is place and route. You place all those logic block in this, okay, here, okay, and then you route it, okay. So this is place and route. You see how it is routed. So this is translate map place and route. After this what you have is yeah, as I said, you have this here after this step you do all this static timing analysis and timing simulation. It is nothing but kind of you do the full timing analysis. You want to check any input output, whatever IOBs are there, input output delays. You want to check the COB, whatever the configuration logic blocks are there, those delays, gate delays, whatever the interconnect delay are there, whether it is meeting the timing constraint or not, whatever is the timing constraint, right? Whether it is meeting or not. How do you know that? Using this all simulations, static timing analysis and timing simulation. There is something called slack, right? Positive slack and negative slack. These are nothing but a kind of, it is the difference between the actual and the expected arrival time of the signal, okay, and all the setup time, whole time you check over there, okay, during these steps. After everything is verified, now what you do, you compile, you go to next step where you generate the bit stream. Bit stream is nothing but it looks something like that, what I told you, right? What is inside the FPGA, nothing but ones and zeros. And now once you have this ones and zero, so whatever your hardware you have, right, whatever target hardware you have, you can configure it using any programming method, JTAG or USB, whatever you write, okay. So this is complete FPGA design flow, okay. Now with this do anyone have any points? Hello.
Hi, Praveen.
Yeah.
Am I audible? Yeah.
Yes, yes, yes.
So just one question on the last part, that B stream, where you expect that one series of ones and zeros created out of it, right? Is it does it give you the binary file out of it in the end,
Yes,
which you
yes,
can
yes.
flash
True,
into the
true, true,
firmware?
true. So
Okay.
based on Nandini, so based on whatever tools you are using, right? Vivado tools, right? It generate your some kind of MCS kind of format. It is nothing but a kind of a bit stream file, binary file.
Okay. Clear. Yeah.
Yeah, so based on different tools, so far I know Xilinx I have worked on. So when you generate this bitstream file, the format is .mcs, okay, .mcs. For Vivado,
Okay.
it is something else. Sorry, for Altera, like Intel, it is something different, okay. But it is
NCS
not.
stands for?
Sorry,
Dot NCS stands for?
that I think I will check. I will check. But it is kind of some configurations. I don't know. I mean, these
Okay.
are, yeah, that is a format .mcs. I will tell you maybe at the end. Let's see.
Okay.
And
But
now
that is the last file we get, which we
that
flash
is
into
the
the
last
firmware,
file.
right?
That is the last file MCS, and then those MCS file. Okay, so whenever you want to program, let's suppose I have this hardware, right, and you are writing the configuration file. Okay, so from you I will just ask, oh Nandini, can you give me the .mcs file? That is enough for me. I will flash those .mcs file here FPGA. and it will start working as whatever the requirement was there. Okay, so .mcs is the last file for Xilinx, but there are different okay vendor, like I say Intel, Altera, it is different format. Okay, but it is nothing but a British. Okay,
Yeah.
okay. Now with this, you already know what FPGA is. I also told you about all the logic blocks, IOBs, switch matrix, design flow, right? Now with this, now what is the strength of FPGA, right? Mm, whether FPGA is having edge over GPU, CPU, ASIC, whether FPGA is having better performance and lower latency than MCU. So these slides talk about this. So as you, I think, as you seen, right, one of the things that you can do with FPGA is you can perform the task in FPGA using parallelly. I mean, you can configure the hardware, right? You can configure the hardware in such a way that whatever the instructions are there, or whatever the programs are there, it can execute in parallel. Okay, so whenever something is executed in parallel, right, you will have a better like faster execution. For example, you see here, right, that is why you call it, I call it as a programmable hardware. How do you are achieving it? By by configuring the hardware, you see. So if I have to implement these circuits using some microcontroller, right, let's suppose these are inputs A, B, C, D, E, F, G, H. So you see, if I have to implement, so first these are getting multiplied here, adding, and then again the output of this is getting added. So if I use MCU microcontroller is nothing but it process the information, or it process the instructions sequentially. Okay, so if I say to process this task, okay, it takes 5 nanosecond. Okay, for this 5 nanosecond, for this 5 nanosecond. So FPGA can do this like activity like multiplication, addition in 15 nanosecond only, 15 nanosecond. But if I have to do the same using MCU, because they process the information sequentially, so first they will do this. You see what is the delay in MCU? So that is where FPGA is better. If you want to, wherever you are using some applications, right, where you want to process, right, whatever the next batch of information is there, right, you want to process very fast, right. So there FPGA play a great role. Okay, other point is reconfigurable. I think I already used so many times what is a reconfigurable. It means nothing but you can reconfigure your hardware, right, or the circuits for different functionality, which is a very a good advantage, right. People might see, right, ASIC, right, ASICs although have an advantage of over FPGA in terms of lower latency and better performance, but ASIC is nothing but it is the functionality is fixed. Okay, that is why we call it as a application specific. The functionality is fixed. It can do only one functionality. Let's suppose I have to convert the PCI bus to the local bus. I can use some ASICs, so it will do only that function, PCI bus to local bus. Now we have, if I have to convert USB to RS-232, I can do with ASIC. No, I can't do. But if I have a FPGA, of course, I can use for PCI to local bus, I can use for USB to RS-232. So in that way, FPGA are reconfigurable. Okay, so that is one strength of FPGA. Of course, better performance it has. If I have to compare, right, the performance per watt, okay, per watt, whatever the power it is dissipating. Okay, so what is the optimal performance? So of course, this FPGA has 3 to 4 times, okay, less than that of a GPU. The low power consumption, okay, of this FPGA has nearly 3 to 4 times less than the GPU or the CPU. So it has a better performance in terms of power, lower latency. I already told. you can execute your sequence of code in parallel using different design styles. Okay, you can achieve those lower latency, faster time to market. You see, there is nothing. I just I buy this PGA chip from any vendor, whether it is a Xilinx. I do the TL coding and then I release in the market, right? With different functionality. You see, there is nothing kind of oh, I have to go to a vendor for tape out or kind of just like ASIC, right? You have to do the logic design, front end design, back end design, then tape out, then verification, validation, different thing. Here it is very simple. You write the RTL code, do the simulations, flash it, and then just you can release it using some you do some verification and you release in market. Very quick to very quick turnaround time. Okay, simpler design cycle. As I say, nothing like ASIC, right? You have front end design, back end design, and then all those tape outs, different verification steps are there. Okay, so here the design cycles are very simple. While what I talk about, right, FPGA design flow, adaptability, yeah, of course you can implement different thing. Even in Xilinx, you can implement the microcontroller, whatever the microcontroller you want. Okay, you can implement a CPU inside this FPGA. So see how it is, how advantage it is, right, in terms of adaptability. You not don't have to worry about OS. Unlike the CPU, right? If you are using any CPU, right, you have to worry about Linux. Linux is there. If you are using any operating systems, right? So although maybe a CPU or GPU, if they have the comparable latency and power, right? But that advantage get over I mean maybe what do I say, that gets law overwritten by this OS in CPU and GPU, whatever you use, right? In FPGA there is no OS kind of thing. It is just RTL code, you flash it, that's it. So these are the FPGA strengths, right? With this, now, how do you choose FPGA for your design? Okay, so you already talk about what FPGA is, what is the design flow, what are the FPGA strength. Now, should you use FPGA in your design? In what are the what are the steps that you should check before choosing FPGA for your design? Okay, so what you see, right? Whenever you are doing kind of a design, right? The initial level of design. Okay, so you have all the requirement. Okay, so look at all the requirement for project. Okay, what is that requirement? I will talk about that. Okay, I will give you example. Look at all the requirement. Is there like a kind of a very complex application, some custom interface you need, some custom interface, or some complex application, some processing is there. There is something talking about timing. Okay, so you see all the requirement whether you need a PG or not. Then see what are the available solutions that satisfy requirement, whether it is a FPGA or whatever FPGA are there, right? And then you decide the requirement, which requirement is more important, whether it can be cost, power, or some whatever the interface are there. And then you narrow down your choices. Okay, so there can be different FPGA, right? It can be from Xilinx, from Intel, from Lattice. Even Xilinx has different portfolio of FPGA, right? With different kind of IOs or different logic blocks. Okay, so how do you select the optimal one? You have to select the optimal FPGA that can do the job. You cannot select anything that will be over design. You have to select the optimal, right? And how do you do that? First, whatever the requirements you have, you do the what is the IOs you will require. Like do in my design I need like a deep switch, I need LEDs. For that, what is the IOs I will require? Am I using DDR? For that, what is the IOs I will use? Am I using flash memory? What is the IOs I need? I am using a touch panel. What is the IOs I need? Some clock. What? So first you calculate what is the number of IOs or the pins. Okay, the pins you need. Okay, so once you do this IO count, The other is hard IP block, intellectual property. This is hard intellectual property. There are two IP block intellectual property. One is hard and one is soft. Soft means it can be synthesized. Okay, it can be synthesized. But hard IP is you cannot synthesize. It means these circuits are fixed. These circuits are etched into the silicon wafer. Okay, those are nothing but kind of a transistor. You cannot change. Okay, but there are many vendors which provide this hard intellectual property. So just see in your design whether you are using some DDR. Okay, so for just see whether any intellectual property is available. You need that, like DDR controller, IP block. They provide free of cost. Okay, so that is a very good way. You can use just interface a DDR with the controller. Okay, IP. So serializer, deserializer IPs, intellectual property. If you are planning to use Ethernet, okay, high speed Ethernet interface like 10 gigabit per second. So there is something called XFI. You see whether XFI intellectual property is there or not. Okay, in that FPGA, okay, it is supported by that. If you are using some PCI Express 3.g, if you want 8 gigabit, whether that PCI IP is there or not with that FPGA. So make sure, okay, that all these are there or not, whatever you need. Okay, the next is the resource. Okay, so basically what I do, right, whatever the requirements are there. Okay, basically you can whatever what you can do, you can write a kind of a dummy, not a fully functional, but you can write some kind of logics. Okay, and then you can synthesize. After synthesize, what the tools will give the kind of a resource, what is the resource utilized by writing those logic. Okay, so resource is nothing but what is the slice. I talk about slice. What is the number of slice you will use. I talk about SRAM, right? What is the RAM you will use. These are some DSP slice, which is nothing but a multiplexer. These are some PCI Express, GTX, GTH. I told you, na, GTH, PCI Express. If you need total IOs, okay, how much you need, user IOs. Okay, I told you about this. So these are IO banks. Banks. I will talk about banks. These are user IOs. Okay, you can connect this all this. So you try to see how many. You see there are different devices. Okay, and different devices, different logic cells, block RAM. You cannot use like, oh, I will use which is the highest one. Then there is no use of engineering, right? Every So you have to select the optimum one by doing all these engineering. Okay, so once you have IOs count and you see, okay, any intellectual property I need, what is the resource I need, like logic block, RAM, slices. Okay, then whatever the industry you are, whether it is automotive industry, military are more like a robust. So there the temperature grade are more higher, minus 55 to 125. There are different FPGA which supports all these different range of temperature. Okay, now if I am using for military, right, I have to select the FPGA that can sustain this temperature. Okay, now with this, of course, cost is the biggest factor, right? I think in industry, whatever we are designing, right, we want to give it to the customer at a lesser cost, because cost is a bigger USP, right? Selling product. Okay, how much cost you can afford, right? Because these APG are costly device, like they are like maybe I don't know, seems like $80 or something kind of. You can check. So how much cost you can afford? Okay, does and if it is costly, you may ask yourself, does FPGA make sense? Like they are usually higher cost. If it makes sense, you need to ask this. Okay, other thing is some miscellaneous, right? The boot times are there, right? With respect to FPGA, so FPGA are based on these technology. They are SRAM based and these are flash based. Flash based boot times are basically faster. That is why we call it as an instant on. So you can see what you want to select, whether SRAM based or flash based. There is another one also, anti-fuse. Okay, there is something called size. What is the size of FPGA you want? Okay, the ball pitch. Okay, ball pitch. What you want? Okay, pitch is nothing but the distance between one pin to another pin. So you have to see this all power, okay, in your design, whether that FPGA device, whatever the hardware you are using, whether that is running from battery or some power supply. So you have to see whether your design run from battery, because FPGA needs power, okay, more power. So you have to see, is it going to be a problem? FPGA, since these are doing some very complex application, there will be, you have to decide for a thermal solutions, whether using any heat sink or heat spreader or some cooling mechanism, liquid cooling or whatever. Okay, but don't worry. These tools, whatever FPGA tools you will give, it will give you the estimate of power. Okay, whatever power it will consume, it will give you. So from that you can estimate whether heatsink is required or not. Operating frequency, how fast you want your FPGA, right? So anything like on below 100 megahertz is fine, but if you go for more than 100 megahertz, I think the design become little bit more complex, in the sense that you have to take care of timing, everything, timing simulations, all this, because instruction are really executing at a faster speed. You have to take care of all those timing, and also during hardware design, okay, during layout, you have to take care of that. Okay, also you have to check, right, what is the whatever the IOs are there, right, whether they are able to support those speeds or not. Okay, so there are different speed grade of the FPGA. You can see it comes with dash 3, dash 2, dash 1. So the more the speed, the more the cost. So everything comes with cost. So this is how you can narrow down, okay, using this all methods, you can narrow down your FPGA selections. Okay, anything else? Okay, so we have talked about this. Okay, now there are some design consideration. Okay, there are some design consideration whenever you are designing a hardware, basically FPGA hardware, right? So FPGA comes with FPGA comes with a different power rails. Okay, it requires a different power rails, like 1 volt, 1.2 volt, 3.3 volt, zero point 0.6 volt, because it has different logics, like the PLL. There is a block RAM. There is some ADC. There is some core voltage. They require different power rails, and to function or to boot up the FPGA correctly, whenever you are booting, to function correctly, each power rail need to rise, okay, or they need to boot up, or they need to turn on sequentially as per the design guideline. So you have to have a proper design mechanism for this power sequence. Okay, you can see here, this is some power rail which goes high, then after some milliseconds, 5 milliseconds, this goes high. Okay, so this power sequence you have to have in your design, and you can achieve this using different design methodologies there are. Okay, of course you have to think about configuration. Okay, whether you, whatever um, configuration you are using, okay, whether it is a quad SPI flash or NOR flash, you see how you are connecting to these FPGAs, pattern FPGA. Other is a reset topology. Okay, so these are logic circuit. Okay, there can be conditions where you want to reset the FPGA because of some malfunctioning or some kind of the FPGA goes into some like it get stuck, right? So there are different logic you write to reset, right? So there is some brownout condition. Okay, like the voltage become lesser than some threshold, so you want to reset the circuit. Those are called brownout condition. There is software reset. So for that you have to implement the reset topology. There is something called mode in FPGA. How do you want to operate it? Whether it is the master mode or slave mode. Okay, slave select. So there are, say, M0, M2, M1. You have to decide it. Okay, using some pull up, pull down. Okay, there is a clock where you want to clock. Okay, there is MRCC, SRCC. These are, MRCC is nothing but multi region clock. Usually we connect a clock over this MRCC. because it can support multi-region. Okay, I talk about IO bank. IO bank are nothing but in FPGA there are different banks. Okay, bank 15, bank 34, bank 16, different banks, and each has its IOs. Okay, so you see the data sheet, and where you can connect all the LED switches. Okay, based on that, and you use now you also want to see how you program the FPGA, right? Using a JTAG, you need a JTAG cable, right? So there is a see how it is connected. This is data out, data in. JTAG is connected to FPGA and then FPGA to RAM. Okay. Okay, I will skip this FPGA to microcontroller. I will directly go. Okay, how do you choose the right one for your project? Whether you want to use a FPGA or a microcontroller. So how do you decide it? As I said, okay, know your requirement. That is very much important. Okay, and then the what is important, right? There can be requirement like cost, power, everything. You know the you see which one is most important, number one, and then you see the solutions. Okay, there are different solutions. Okay, you see and pick the best, whether the PGA is best or the microcontroller is best. For example, you see this is one example, right? Jack, he's asked for doing a task, and what is that task? So he's asked that you make a circuits or design a circuits or embedded system that take a high definition, high digital quality image data from computer. Okay, filter it out and then send to some display. Okay, OLED display, and these are the requirement. Okay, requirement, you see what is the requirement? Some custom interface you need. Okay, custom interface you need. Okay, so what was the task? Taking a high digital image from computer, you filter it, send to a OLED screen to display. So what was the requirement? Custom interface. You see there is data, high speed data. It means there are lots like 5 MB, 10 MB data, high speed, and then you have to filter it. Do some lots of maths are there. Okay, and then you send it. Okay, to display. Lots of math are there. Custom interface, low power, cost. Okay, so these are requirements. Okay, now what is the best for this? Okay, there is a custom interface, math, low power. Okay, requirement 3 is low power, cost is very less, like I mean requirement 4 is cost. You don't worry about cost is okay, but you worry about this custom interface should be there. It should support a lot of math. Okay, low power. Okay, you worry about these, but you don't worry about cost. So I think the winner is FPGA. Okay, and if you see the headset, VR headset, Oculus Rift, they are using the FPGA inside, and this is what the task is. Okay, there is another example, Russell, right? He is asked to take the ultrasound sensor data. There is ultrasound sensor. You take the ultrasound sensor data and determine distance. What is the distance between the ultrasound sensor and the object? Okay. Requirement one was you need a proof of concept in 2 months, a very less time. Cost is also one requirement. It should be lesser cost. Third requirement was low power. Okay, a requirement, this was like basic math can be slow. This was not like okay, even it is slow, it is okay. Okay, so here the winner is microcontroller. Okay, so you see this autonomous Amazon autonomous delivery, they use this microcontroller, because here you cannot use FPGA because your requirement says you don't need you need basic maths, and you also don't worry about power. Power is cost. Okay, so microcontroller is fine. With this, the session is over. Any questions?
No problem. I don't have any more questions. Will you be sharing this